Sure.
Okay. Thanks everyone for joining, and thanks Changchi for being here to showcase your project with us today. And I mean, I don't really have any housekeeping items, so we can just jump right into it. Okay, I'll give the floor to you, Changchi.
Sure, thank you, Hannah, and thanks everyone for joining us today. I guess let me just display this. So yeah, my name is Changchi. I'm going to talk about like a small demo of a small task that I have been working on before, leveraging machine learning to solve some like real problem. Hopefully can give you guys a sense about like how you would tackle a traditional problem with machine learning technologies from scratch. So a little bit about myself. I'm currently working as a machine learning engineer at e-commerce domain in Singapore. And specifically, I'm working on the search and ranking team. Previously, I've been working as a data scientist for a few years, including in the oil and gas industry and also agriculture industry as well. So it's kind of a switch between the traditional industries to internet industry. Working on different topics as well, on optimization, data mining, and also including some deep learning with imagery data and time series data before. So yeah, I would say like every time I switch to a team or project, I feel like I'm just a total beginner. I need to learn a lot of new stuff from scratch. So if you are into data science, or you want to have a career in this, so don't be surprised if you always miss some new stuff. I think it's a very interesting and also challenging thing in this domain. You always like just need to keep learning and to touch some new things and improve yourself, and that's quite interesting to me. So yeah, without further ado, maybe we can start with some very principal data science pipeline or life cycle, and then we can jump into our small project today. So I guess I think most of you have been into some other workshop or presentation before talking about big data or data science, and you may have seen this workflow like 10,000 times. So we all know about that, like data product usually start with some data engineering, and then we go into a data science to do some actual modeling or statistic analysis, and then we serve our conclusion or our model, right? But I think the difference is just that many times when you see this pipeline or workflow, you may see that classic icons image, like showing a lot of small icons at the background. Like for the engineering part, you may see Sparks, HBase, right, MapReduce, and SQL database. And for data science, you may have seen Jupyter Notebooks, sklearn, and TensorFlow, a lot of those small icons here. I just didn't put it here because I think those are too much information for a lot of us, because obviously you don't have to be a master of all of those tools. I think they will be very useful for you guys if in the future you are into a job position working in machine learning or data science, or you need to handle some big data or models, right? They will be very, very handy for you. But if you sometimes feel confused or overwhelmed about that, just don't worry about that. You don't need to be a master of all of these tools. If you really needed it in one of your project or in your position, then it would just take you no more than 1 or 2 weeks to get familiar with that and leverage them in your day-to-day work, right? So, but yeah, I think depends on different teams or companies, or I think your workflow. But if you are working on a data product, then this will be a very general pipeline that you need to do some data engineering, data science, and data serving. And also you can like see from this pipeline that there are a lot of different domains or topics in this data product topic. So that's why nowadays you can always hear a lot of job opportunities in this domain, right? So you hear about data engineer, data infrastructure, data scientist, data analytics, or even business intelligence, right? So they're all in this data family, and because because in the data domain there is that many different aspects of works needs to be done. So they really requires different expertise. So if you are into a career like this, you may start to think about which direction you want to really grow your expertise and what type of data specific job you are looking for, I guess. So yeah, I guess in this workshop before, there are some different topics talking about Airflow, Plotly, Dash. I would say they are very, very useful for a data product in terms of engineering, like scheduling your data job by Airflow, or displaying your final output or analysis or report to the users using Plotly, right? But I would say those are mainly focusing on the engineering part or the last serving or storytelling part, right? So today, I guess our focus will be on the science part, which is in the middle, talking about more about the machine learning algorithm and also some use case, some actual model development today. And if we expand this science part into details, usually, I'm not sure how experienced are the audience here today, but if you have worked if you have worked with any machine learning task before, no matter it's from a class or from a real world project, you usually deal with three things. One is the data, then you have the model, and then you want to tune your model to improve the accuracy, which we usually call a metrics, right? So I think we heard about a lot of saying that, hey, when you work with the machine learning, 99% of your effort will be handling, cleaning the data, collecting the data, and doing some engineer on the original raw data. And that is correct, I would say. It's just very important to get a good data set before you really get into machine learning or statistics. So here on the left part, the data, including how you get your feature, how you get your labels, that will, based on my experience anyways, that will take the most of your effort and your time in a project. And then once you think you're ready, you got a good enough data set, then you can get into the statistic part and the modeling parts. That is, we learn a lot from the machine learning courses, including online resources or maybe offline from your school, talking about, for example, neural network, random forest, logistic regression. We have heard a lot about these names, right? And this is all about in the second step, which is modeling. So you basically apply all you have learned from school or from whatever resource to apply those algorithms to handle your data. And then what is the objective here is to improve your metrics, which is the third part, right? So usually you have a problem, then you define what you want to achieve. For example, accuracy for classification problem, or maybe you want to reduce the RMSE for a regression problem, or or if you're working on a fraud detection problem, then you may be very concerned about your AUC or precision or recall metrics. So whatever you define based on your case, the whole idea is that you just keep applying different technologies or potential solutions in your modeling part to improve your metrics. So yeah, without further ado, then let's just take a real example to understand what I'm talking about when I talk about like previously the data model and metrics parts, right? Because I think maybe some of you have heard about Kaggle, which is a very good data science platform to work with some real open source data sets. And also maybe from school or from the seminar, whatever, you have dealt with some machine learning tasks before. But oftentimes is that you're provided by a fixed data set, right? So some people has done this heavy part for you. So they have done everything into maybe Excel file, CSV, or database for you, and just tell you, and they also give you the metrics. Hey, I want to improve the accuracy, I want to improve the RMSE, whatever, right? So you basically just need to focus on the middle part, which is the modeling. That will make our life much easier for sure. But in the real world case, that's not usually that lucky enough to get a very beautiful data set for you to just jump into modeling, right? So in some projects, or like especially in the real world job position, most of the time you will have to collect the data by yourself, clean it by yourself, and you sometimes need to define your own metrics to make sure your product is making sense for customer, right? So today, let's just take a case study here to see how we can think about like how to formulate a problem into a machine learning problem and how to tackle that from scratch. Okay, so this is a case study. So let's say we are building a search engine for recommendation system, which recommend restaurants for users, right? However, these restaurant candidates, they are from two different resources, or you can think about a database, they are from two different databases, right? So if you look at the two figures there on the left-hand side and right-hand side, all the information we have for the restaurants is that the restaurant name, the city, the region, and their address, their rating on the app, and their postal code, right? So let's just make it simple, just 6 information there. So in the sense of a search engine, you definitely don't want to show duplicate result to the users, right? For example, like if a user search for a fast food restaurant, and you show them like 10 examples, and 5 of them are pointing to the same McDonald's around, right? So then that would not be a very good search engine or search results, right? So all we want to do is we want to avoid showing duplicate results. So if you look at the 2 graph below there, you can see we have massive of candidates, restaurant candidates there in 2 different databases. And some of them, which is in the red circle there, some of them are actually the same place, but they are probably just registered on a different database or a different supplier or something like that, right? So the task here is that imagine you have such a big CSV or database which has millions of rows. Some of them are not overlapping, but some of them are overlapping within your database, like this one, the Temple Beach house, right? So for example, they can have a exact same name, but if you take a look at this example on the city side, right? They call themselves in a different location, right? Or maybe just a different definition of the city or the location, right? And you can also see some other features are different too, like the ratings as well. So this is just one example. We can see more example in the later part of this presentation. Sometimes you can have a totally different restaurant name at all, but they actually represent the same property. So I think it's very important now for you guys to take like maybe a minute or so to think about if you are the data scientist or you are the engineer who is working on this problem, what would be your solution? So remember, previously we talked about we have data, which we have features and labels, right? On the left part, usually a lot of people provide this for us. But now, given this data set or problem, we don't really have a label. So, right, so we need to design it by ourselves. And secondly, we don't really have good features. So if you think about these 6 columns in your database, right? They are pretty much free text except for the region and the rating, right? So they are not a very handy features for you to just jump into your model maybe, and you don't really have a metrics now. So So we are not talking about, hey, you want to improve the accuracy or whatever here. So the task is just to find these duplicate records within a massive database. So I think it's probably good to take a few seconds or minutes for you guys to think about what would be a solution. And if you like, please do not hesitate to raise the discussion here. Any idea or any questions so far about how to solve this type of problem?
I have a quick question. Like, can we search that restaurant online to double check what it is currently located?
So you mean as a product, right? I don't think that is very useful because you are building the search engine, right? And we probably don't want our product to rely on some other search engine, right? So if someone search on your website and then at the back end you pass this query to, let's say, Google, and then fetch the result and then return to the user, then it's basically not a search engine that we build, right?
There are two cities, like they're different, but which one is the current one? We need to like double check with that first, and then remove the like redundant one and keep the correct one, or like modify the information for either one of them.
That's a very
I'm
good.
Just curious.
No, that's a very good idea. But however, like sometimes I think this is just one example. But sometimes, because you can see the region, we have restaurants from all different countries, from China, from the States, from Australia. So sometimes when the city are different, that doesn't mean one is wrong or one is correct. Maybe they're just like some local languages, like to represent this real location. You know what I mean? Like for example, New York, right? In the database one, maybe you can tell New York, but from a second database, maybe it's just NY. You probably can't tell which one is correct or which one is wrong because both of them are correct. They just have a different presentation here, right?
Yeah.
Yeah, that's a good thinking though. Yeah. Any new ideas about how to formulate this into a machine learning problem? So if you think about previously what we talked about, right? Before we actually model, we need two things, or basically three. One is the features, one is the labels, and also the metrics. Metrics is that we need to know what we are doing here, right? So what we are dealing with today is a classification problem, is a regression problem, or so we basically need to define the success criteria for ourselves to get a model, right? So maybe I would say when translating this problem into machine learning problem, we need to think about three things. One is how to generate our features and how to define our label. And number three is how to define our metrics, right? Okay, so is it any new ideas or any input before we move forward? Or any questions is welcome too. Okay, so if no, I would just go ahead to present the solution that I had when I tackled this problem, right? So first of all, it's not a standard solution, to be honest, and it's not any fancy technologies that I'm going to showcase. It's just one potential solution for this problem. And I will just put this in front that there is a very big shortage of my solution. So hopefully you guys will find it out and we can discuss at the end of the presentation, okay? So yeah, so first of all, we just have a massive database with random rows of restaurants, right? How I tackle this first is I think it's very, very hard to like find these row by rows in millions rows of database, right? But when I look at this data, I figure, okay, the name, the city, and the address, they can in like totally different formats, right? But seems like the region is actually kind of standard, right? And it represents usually a country or very big region. So the first assumption I made here is that, okay, I I assume that the information in region is correct. Okay, so it's possible to happen, but I think it's very unlikely that you put a restaurant into a different country, right, or region. So that will reduce a lot of search space. If you think about that, for example, I have 1 million rows, and now I want to find the duplicate of this restaurant in the database. Instead of going through to compare 1 million records, right? I just need to compare those records in AU. I believe it's Australia here, or Austria, I don't know. But that this assumption will reduce a lot of search space in our problem. So that's the first assumption that I made. Okay, so with this, now what I want to do is I want to basically find the matching rows within the region, right? And then let's just jump into our next one. Sorry. Yeah. So this is exactly what I'm talking about. So we want to define the feature labels and metrics, right? So for machine learning, as all we know that how the model can learn is they will learn from some human knowledge, right? So we will have to generate some label sets there. So for example, if you are the data scientist working on this project, then you have millions of rows in your database. Then what you may do is that you need to input some human knowledge before you train the model. So that is manually create some labels. For example, 100 and 200 rows should be good enough, right? So the first thing we do is that we should provide some human knowledge by creating the labels. That is filtering by the region first, and then maybe create like some one-on-one match before we train the model. And based on this information, it should be kind of simple to do manually to find 100 or 200 rows, because if you look into the names, right, sometimes they're different, but most of the time, if you search by the keywords, then you should be able to find the duplicates within this database. So considering millions of rows in this database, maybe finding 100 or 200 rows within this database is not a terrible effort. Or is there any questions there? Okay, I'll just go ahead then. So yeah, so first thing, I create my labels by manually finding some examples of duplications within my database. So with this, I can tell my future model, hey, these are the actual matching records, right? You should learn from my knowledge, from my human knowledge, and then apply the same knowledge to the other 1 million rows in the database, which make my life much easier, right? And then, so now the problem for the model is that, okay, now you have seen some matching problem. You want to predict whether or not 2 rows are same or not, right? So my matrix now is going to be a classification problem. So I want accuracy to be higher. Okay, so let's just take a quick look about some correct mapping examples. So this is something that I manually do, for example, right? Imagine that I manually do like 100 rows or 200 rows within a million rows database, right? So this is some correct examples of duplication in our database. So for example, I think the audience who just raised the question about the city difference, right? So for example, this blue row, right? You can see they are actually the same restaurant, but on our database, they represent as a different city. Sometimes it's hard to tell whether or not it's correct or wrong, because maybe these 2 names are representing the exact same city. And you can also see that, for example, okay, so if you look at the first row, this will be a very simple case for a model or a human to detect, right? Because the names are the same, city are the same, and everything is pretty much the same. But the second row, if you look at that, there can be different definition or different naming preference in different database, right? For example, this one called a dual restaurant, but this one I think is using a local local language or whatever to represent the same restaurant name, right? And then the third row, this example, they actually change the city, right? And the fourth example here, if you look at that, so the name here and the name here, actually the keyword are the same, but they just remove the restaurant word in the name, right? And if you look at the address, they are pretty much the same thing. But if you only rely on your address, for example, the last example here, the address can be totally in a totally different format or representation, even though they are talking about the same thing, the exact same location, but they have like different words to represent that, right? So basically, looking at this example, right, one information we can get is that, okay, we can look into the name, we can look into the city, the address, or maybe even the postal code to find this mapping, but it's hard to rely on only one source. So we kind of need a model to know when to rely on the name mapping, when to rely on the address, and when to look into the city name to find the match. Okay. So with this manually labeled data set, we pretty much figure out the label, and now we know we are dealing with a classification problem. We want the accuracy to be higher, right? And then now it's all about how to get this feature and how to let the model to learn this human knowledge, right? And from here on, I will switch to IntelNova, which have some actual coding that I've done for this project, and some visualization and some intermediate results. Okay, I've hidden all this code, but if you are interested to look into the code, just feel free anytime to stop me or shout out here. I can totally like open this and show you how I run this analysis. Okay, so
Changchi,
given,
can you zoom in a bit?
Oh yeah, for sure. Is there a way to do it? Oh, yeah.
Okay, thank you.
How about now? Is it better now?
Good. Yeah, thank you.
Okay. Yeah. So just a review of the approach that I mentioned just now, right? So we assume that the region information is accurate. Then we can do the human one-to-one mapping for 100 or 200 examples, right? And then we translate this problem into a mapping problem that is given a pair of hotels. We need to classify whether or not they are the same place, right? And then for the feature we talk about is about the similarity. I will use a lot of similarity as a features to train our classifier, right? We will go into that step by step. So first of all, after we manually label, we want to check some label data first, because as a machine learning engineer or data scientist, the first thing when you get a data set, the first thing you want to do is actually visualize that if possible. Because sometimes if you deal with the text data or image data that like, for example, it will be very useful for you to actually look into some details, and then you have a sense about what this database is talking about, right? So this is just the screenshot that I just showed you in the PPT. These are some correct examples that I manually did to match, to tell the model, hey, these ones are good. So you should classify this type of examples as a good match. Otherwise, you should predict that as a non-duplicate, non-overlapping examples, right? So the second thing I do is some data cleaning, which is a very big part of our work. So if you look at this one again, visualize your data, what potential problem you will have before actual modeling. So now we want to extract the features from this information, right? What are the features? They are free text. Free text is pretty hard to handle directly. For example, maybe we got lucky on this example, right? So the name is exactly the same. But imagine, what if this cafe, this word, the C is a lowercase, right? For computer, it would just tell you these are different words. So this is one simple example we need to deal with. some other example is, for example, if you look at the edges here, right? From a human eyes, it's very easy to tell, hey, these are just talking about the same thing, right? But for computer, if you just input this free text into the computer and saying, are they the same thing? They will tell you it's not, right? Even though it's just one word extra, or like just a lowercase, uppercase difference, or whatever, this slash, or maybe just a space in between, right? Or just a different definition and address, they will tell you it's different. So the first thing we want to do is we want to standardize this information. That is data cleaning that we want to do. So I don't think I have included all the good solutions, but this is something I have done for this data set. So first of all, I removed the stop words and punctuations in this free text. For example, those commas, those slash, those non-useful information, because we don't, as a human, right? When we look into the comparison by our eyes, we don't really rely on these commas or stop words or slash, right? We more care about the actual content of the text. So I remove this one first. That will make our later work easier. And then I convert all the text into a unified encoding. For example, like because we can see this data is coming from different countries. So maybe sometimes they will be represented in French, in Spanish, or like in some different local languages as well. So I standardize them by using a unified encoding format and convert all of them into lowercase. And then also, if you look into this information, right, later on, we want to compare the name. How similar are the names? How similar are the edges? And then by just looking at this data, we realize that there are a lot of overlapping information and not useful. For example, restaurant, right? We know that we are dealing with the data set of restaurants. So of course, like in most of the name, maybe 99% of the name, they will have this word restaurant in their name. So would you say they are similar if two names both have restaurant in their names? Probably not, right? Because most of them will have the same word here. And also same for the address, right? We usually see the street, we will see probably the road or whatever these common words there, right? So you would not say two addresses are the same only by looking at the road or street word, this single word in this free text, right? So this I would say is not useful information. So what we want to do is also avoid looking too much into this information when we do the modeling part. So the third thing I did is that I get a word count for each individual word in our entire corpus, and then remove top 10 frequent words from the names and top 50 frequent words in the addresses. And this 10 and 50, I would say, is not the optimal solution for sure. It's just something that you can find out through your experiments, right? You change different number and then see what's the performance. That is your experiment, right? So up to now, you may be wondering, hey, so this sounds like a very expensive work because you need to remove all the stop words. How do I know which is the stop words, right? And do I need to go through row by row to remove this punctuations? And how do I get the word counts of this like individual words into millions of records of addresses, right? But luckily, we actually have a lot of built-in tools in Python or whatever language you use to deal with this natural language or free text, right? One of those I would recommend here is this one, Nltk. It stands for Natural Language Toolkits. So I will probably try to find out row to show you how to use this. Yeah, so I'm not very much into the coding parts, but if you really want to learn, you can always search and then go into their documentation for this toolkit. It's very handy and useful. Basically, with this, you just call very simple command and input your text. For example, normalize that, right? So this is the function that is inside this toolkit, right? You just put your text there and then tell him tell that to normalize it, to encode it, to decode it, to lowercase it, and then to make some translation from whatever punctuation you want to remove or digits you want to remove, then it will do it for you like in no time. So don't worry about to write too many code to pre-process that, because nowadays machine learning or these toolkits are pretty handy and very ready for you to use it. Okay. So yeah, after we apply this, removing the stop word and unifying the format, let's just visualize our data again, right? So this is the data that I get after those processing, right? So you can probably see what's the difference compared with what we have seen before. So all the words now are a unified case, are lowercase, right? And then there's no slash, no like punctuations, no digits there at all, because I have extracted it out, right? So right now it's just free text, like looks pretty normal. And then we also did a word count for all the keywords in the restaurant names and the restaurant address, right? And if we visualize that, we will find that, okay, so in the restaurant names, these are the most frequent word, right? The first one is restaurant for sure, and then food court, kitchen, fast food, cafe, whatever it is. And then in the address, these are the most common words that exist in our data: road, street, district, RD, whatever it is, ST, drive. So that basically means, I just visualized the top 10 here, I believe. So there are for sure like hundreds of thousands different words in our documents, right? And if you really look at all of them, this is a very long tail distribution, but you can totally see, hey, restaurant is like it appears 8,000 times, and then these words are definitely going to be very common in our database. So you do not want to consider them when you want to compare to address or to restaurant names, right? So what we want to do is that we find out, okay, these are the most frequent words, and then we want to get rid of some of these frequent words, right? So get rid of them are pretty simple once you find out these words, right? Because now they're all unified into lowercase and a standard case. So you can basically just replace this word with an empty string in your data, right? Okay, so again, I'm removing 10 frequent words in the name and 50 frequent words from the address. And this is based on my own decision. You can always do a lot of different experiments on that. But the logic here is that I visualize the top 10 saying, okay, up to the first, like maybe 8 or 9 words, they're pretty common. But starting from the 10th and below, there are actually some special words that is not very general. It can actually represent the specific restaurant, right? That's why I select 10. And same logic, that's why I select 50 for the address. Okay, now we replace all these common words in our data sets, and then let's just visualize our data again, right? So compare with the original data set, which has what number of rows or some restaurants in the actual text. That's very easy for human to read, to compare, right? And after the data cleaning now, because I remove all those words, if you look at the address, for example, for human, this does not represent any address at all, right? You probably don't know this is an address. But this is, I would say, is easier for a computer or a machine to identify, because after we get rid of the road, the street, the name, the restaurants, those words, and now if you just compare these two, they are pretty unified, right? After getting rid of those common words, right? Maybe now it's making no sense for a human, but now I think it's easier for a machine to recognize whether or not they are matching, right? So for example, this one is just 100% match, but still we have some problem to deal with, right? For example, we did not get rid of this DR, which does not appear here. And for example, this one, right? There's an actual no there. I think that represent the number. And also for this example, right? It's just still totally different. So even though now we have pre-processed the data and then make it easier for the machine to learn, we still need to extract some more useful information for our model or the machine to to classify that even much easier, right? And then so basically what I'm talking about here is that we want to translate this free text into a real number, 0.1, 0.2, 0.3, or 1, 2, 3, which is super easy for the machine to learn. And this is what I'm talking about generating the label and features, right? So after data cleaning, we merge the two data frames by the country, by the region code. So imagine that in the database, when you do this join, right? You only join by the region code. For example, For example, you join this one based on the Japan code, right? So, for example, you have 10 restaurants in Japan. After this join, how many records you will have? That is 10 by 10, right? That's 100 rows that you will have in after join, right? And within this 100 row, maybe only one or two of them are matching to each other. So those are the positive example for the model. All the others are negative. So the model should learn to predict a negative result for those, right? So this join, one problem of that is that after this join, 100 row, we only have 2 or 3 rows, which is actually matching. So after generating this set, we can look at the positive rate in our training is around 3%. This is a very low percentage, right? So so for example, after, like, think about this, after the join, we could have millions of training examples. Only 3% of them are the real matching in our training set, right? So for example, if your model learned to predict all of them are negative, so you basically don't need to predict anything. You just blindly say, okay, this is not matching, this is not matching for millions of records. Then what is your accuracy? Your accuracy will be 97%, which is a very high number, right? So in this case, what we are more concerned about is the precision or record, or maybe AUC metrics to identify instead of the simple classification accuracy. I believe most of you have some background knowledge about this. So this is just one point to note here, that we have an extremely imbalanced data set, and we need to consider what metrics is useful in this case. Okay. And then after the join, we know there's about 3% in our label set. Now, back to our original problem, we want to generate our feature, that is convert those free text, those free words into actual number that the model can learn. Again, this is just the solution that I proposed when I worked on that is not going to be the optimal solutions. And if you have any further ideas, just do not hesitate to stop me anytime. Or if you have questions, do not hesitate to stop me anytime and then discuss. Right? So this is basically some features that I think will be useful for computer to learn how to classify them, and then I add them as a feature. So first one is the address number similarity. So this is very simple. So looking at the address before, right, we usually see the digit, the number of the street name, right? Let's say 10th road, 15th street, or whatever that. I extract this digit out, and then I compare whether or not they are matching in the two examples, right? So usually if this digit is matching them, I would say it's very likely that they are talking about the same address. And also word similarity. So remember that we have extract all these free text into a single word here, right? Like, even though this one is not a very legit word, but in the processing part, we still consider that as a word, right? We can easily break these free text into different words, and then we can compare the similarity word by word. For example, this word is 100% similar to this word, right? This is 100% match, right? This one is 100% match to this one, right? And for example, probably don't have a very good example here, but okay. So if you look into these two words, they are probably representing a different names of a city, right? Based on their local languages. But how similar are these two words? They probably don't have a very good similarity there, right? So this is something in the model I consider to identify how similar are these two words. And specifically, I'm using an at this distance to define these two words. And also I have, okay, so I use the word similarity to define the city similarity. And then for an address, we have multiple words, right? So now we have similarity of one single word. But when we look into the address, we have multiple words in the address. How do I calculate the similarity between address? So what I'm doing here is using this approach. I use the number of overlapping words over the shortest text sentence as a similarity between the two addresses. So let's just have an example. Let's say one address, they have word A, B, and C, and the other address, they have B and C, right? So these are the two addresses. So my calculation for this similarity will be, so I first look at how many overlapping words between these two addresses. There are two overlapping, right? And then over the shortest sentence, which is in this case is 2, right? This is 3, this is 2. So divided by 2, then is 100% match. So in this case, right, I identify this similarity as 1 because I consider this address have the information that totally contain the information from another address, right? So I would say this is 100% match. And note here that the order doesn't matter. So if the second address is B, C, and B, then it's still 100% match in this case. Okay, so this is one way I identify the similarity, and some other features as well. We have the postal code information as well. So I created one feature is just saying whether or not they are exactly the same postal code. So for this example, maybe it's too easy because they are all the same, but there are some examples that you can actually see are different postal code. You probably don't. Oh yeah, for example, this one is a good match, but the postal code is lacking, is missing in one data source and is existing in some other source, right? So this is just one feature. And also we have the rating of each restaurant. So I define the star rating similarity, which is the absolute difference over 5. 5 is the max rating that we can have, right? So for example, so if two ratings are both 4s, then their difference in this calculation will be 0, right? So if one thing is 0 star, another row is 5 stars, then the difference here based on this similarity will be 1, right? So these are the features. Just take a quick look in the actual coding. Not digging really deep into it, but I define some useful function to identify whether or not it's a typo, because I think in the database, especially for free text, it's very easy to have a typo. For example, like restaurant. Oh, sorry, restaurant is already omitted in our database, but you can say like sometimes you can see a very long word A, B, C, D, E, and then you have a typo A, B, C, E, for example, right? So if you see a word like that, sometimes you may consider, oh, it's just a typo and they're talking about the exact same word. So I define some function to identify whether or not it's a typo. And also I define my function to calculate the text similarity, which I described the method before there. And then also the address matching problem. Then in Python, I'm not sure if you are familiar with Python, but it's very useful to use a data frames or apply lambda function to apply this to every single row of your database, if your database is small enough to fit into memory, right? So basically, it's a vectorized operation. It's pretty fast to generate from like millions of records, right? But basically, after this process, we have calculated the address number similarity, city similarity, clean edges similarity, which is that I just get rid of those frequent words. And after we get rid of those frequent words, we calculate similarity and the star rating similarity and everything I just described previously. Okay, so after having this, the next thing I did is to have a baseline model. So when I look at the actual data by my eyes, right, I feel like it's not too hard to identify the matching row, because you can see like the names are exactly the same, city, same, address the same, then I would say this is the correct match. It's not too hard to learn, right? So the first thing is that I just don't worry about machine learning first. I create a baseline model that is a very naive and straightforward rule. So I defined it in this way. The model predict these restaurants are matching if their name and address similarity are both greater than 0.5, or if they have the exact same name. So this is not machine learning. This is just a human definition of the mapping, right? So if they have the exact same name, I say that they are matching. If they are not exactly the same, but their name similarity and address similarity are both greater than 0.5, I still say they are a good match, right? So this is no learning at all. I just use this simple logic as a baseline model, and I test the accuracy here, and this is the result. So for this simple logic, the accuracy, accuracy here, I mean the precision specifically. Precision is 100%, and the recall, the coverage is 94%. So that means even just using these simple logics, right? All the good matching that we predicted is 100% correct. And within this million rows of database, 94% of the matching records is found by this simple logic, right? So I think this is not a bad statistic or bad result at all, considering we only did a few simple things. We removed those frequent words, we calculate this similarity, and then we apply this super simple logic, right? We already achieved this one. But of course, we want to do something better, right? That's where the machine learning model comes into place, right? We set up the baseline here saying, okay, this is something we can do easily without learning. Then we get into the domain that we are all excited about, it's all about machine learning models. Then we, so what I did is that I get this similarity as a feature, and then I do a K4 validation, train and test my model with different algorithms. Again, I'm not sure how familiar you are with Python or machine learning. Don't worry about like implementing a very complicated model by your coding, right? Everything is ready in these machine learning packages. And specifically here, I'm using sklearn. Maybe most of you have heard about this, right? And what I did experiment is that they provide a lot of different models in sklearn, including SVM, logistic regression, random forest, XGBoost, whatever you name it, you can just try it, feel free, right? So this is exactly what I did in my experiments. I tried different models, I tried different parameters, and then I test the accuracy, which is the precision and recall for all these experiments. And then the result I found that is, in this case, I found that the SVM is the most useful model in this case, and it gives me the best result that we can get to 99% precision with 97% coverage. So that is saying after this model learn this information, we can so in the prediction that it made, 99% is accurate to predict the positive matching, and within the millions rows of data set, 97% of the positive sample is found by this model, right? And then after we train this model, we just test it on the unseen data set. And then, so remember what I showed you before is the record that are manually matched, right, by a human. But now this is the test example. That is the model predict, hey, these are the matching examples. These are the same restaurants, right? And after training and prediction, let's just take a look at the example, how our model is doing, right? So these are, I think, 5 examples that it found that the model predict as matching, right? So for the first one, I think it's pretty easy. I think the model easily learned that, okay, these 2 names are the same, right? And then maybe, is there, yeah, so, and the model also learned something to figure out this example, right? The name are not exactly the same, and I would say is kind of pretty different, I would say. This is control food court on the river, and this is roadway food court and fast food on the river. So I think, yeah, this is quite different name, but the model still learned this because it leveraged some other information. Maybe it's mostly using the address here in this case, right? And this is just 5 rows in the data sets. And I actually test this model on like all the millions of records, and it turns out that the accuracy is pretty high, actually, which aligns with our training statistics, like 97, yeah, 97% in terms of coverage. So yeah, so I think this is kind of the full workflow in this project. So just a quick recap, right? Originally, what we had was a simple database that randomly contains some duplication and mapping problem. And how we tackle that from end to end is that we make our assumption that the duplication should only come from the same region, and then we join them together. We manually create our human label for 100 or 200 rows, and then after that, we define a label, and then we start to clean our data, remove those standardize the format, and remove those unuseful frequent words, right? And then we calculate the similarity as features, and then we build our machine learning model. And after we build the model, we test the accuracy by cross-validation, and then we apply to the unseen data set, and then we again visualize the model prediction for the results. So I hope this kind of give you a sense like how I tackled this problem from scratch, like without feature or label or anything, right? And to this final product that I spend like human effort for 100 or 200 rows, but now the model can predict millions of records in maybe a few minutes, which really saved my life. So yeah, this is kind of the end-to-end solution in this framework. So we all know, again, we all know that the data product have a full pipeline, engineer, science, and serving. And then today we only focus on the science part. And what I present as end-to-end is the end-to-end in this part. So from data, I clean, I engineer my data, I build my model, and then I chose my own metrics and try to improve that. So yeah, any questions so far? Okay, and as I mentioned at the very beginning, before we jump into this project, there is some shortages and some improvement needs to be done for this solution. As I said, this is not a standard solution or the best answer for this problem, right? It's just how I did that when I worked on this task. So now I think it's a good time for you guys to really think about what will be some serious issue or potential like drawbacks on this solution. If you have any inputs or questions, please don't hesitate to raise and discuss.
I have a quick question.
Yes.
So great presentation. Thanks, Changchi.
Right.
Probably this question is not related to shortage, but I want to ask the data source, like how did you get the data from the same platform, like from the same resource or different sources?
There are different resources, as I mentioned here. So we want to recommend some restaurants, but these restaurants are coming from you can think about 2 different suppliers, right?
Mm-hmm.
So
okay, awesome.
That's why they have like totally different tags.
Yeah, because I want like ask about the data distribution thing. If we only consider one source, that could be having some biases. But like you said, you have two suppliers. So yeah, it makes sense. Thanks.
Yeah, no worries. So any other inputs or questions, or if you have found any potential issue there in this solution? Yeah, I think, yeah, while you are thinking, I think I should mention that this type of, so in this case, the data or the use case, honestly, I actually encrypted that. I modified a little bit because due to the data privacy issue and whatnot, right? But this type of task, I think, is very common to not just a data science space, or to a lot of traditional industry or company or teams that can be very useful. For example, fraud detection, right? So I have heard about a project from my colleagues before. He has worked on some similar topic as well. That is to find the fraud application of insurance claims, right? So if imagine that you work for insurance company and you got the claims like every single day, then there might be some fraudulent claims within these millions of claims, right? And like people, they probably just input their name or their short name or their initials as a different people, or they input like a slightly different address to make this claim. And sometimes you may want to identify whether or not they are duplicate, they are the same person, and avoid paying like double for this, right? So yeah, I'm seeing a question in the chat. It's possible to share this notebook. For the notebook, yeah, I can totally share that, but unfortunately, I don't think I can share the data, the source data itself. But for the notebook or the actual coding, yeah, I have no issue sharing that for sure. And I will probably work with Hannah afterward to about how to share this notebook.
So Changchi, can you give us some insights in what you think the potential shortfall of this method is?
Yeah, for sure. So there must be a lot of those, but one very big concern when I work on this is, well, when I work on this is a small task. The problem is to solve a small database, maybe a million rows, which can be easily fit in a CSV file, right? So that's not the case. But okay, now let's say I've got a very good model, and now your boss, your supervisor, whoever, your customer want you to deploy this model onto a system that can process maybe like a million rows every minute or a second, or maybe your database is just much bigger, a billion rows, right? And remember, there's one assumption that we made, that is we join our data sets with region, right? And for example, in this case, I have about a million rows, right? And then I think I remember I have like around 200 different regions, right? So each region you can think about like how many rows in each region in average, right? So let's just do this quick math. I think it's 500K. Is that correct? Oh no, sorry, it's 5K, right? In each region, right? So when you join, so this is 5K multiplied by 5K. It's not too bad. It's not too bad. You can do this join, right? But now, let's say if my company only focus on one country, right? And it's easily to get a million restaurants in this country, right? So if we have only one country and I still want to apply this solution, and now within this one country, I have 1 million restaurants. Now, when you generate your training set, what you need to do is that you want to match 1 million rows with another million rows, right? And this is a restaurant. This is a case for restaurant. Restaurant can be easily scaled to 10 million, or sorry, this is an example of restaurant, but if you think about some other fraudulent detection, for example, it can be a cybersecurity or maybe IP address or anything like that, right? It can easily get into 10 millions or even 100 millions. Now, if you want to match that, then you're going to join this data 100 million rows with another 100 million rows for your model to predict, because my model is, remember, the model input is a pair of restaurants, right? And then we want to predict whether or not it's matching or not, right? So then before you really use this model, you need to join your data first. And in my opinion, when we are talking about the scalability, then it might not be very feasible to join a huge data set, especially if you don't have a lot of resource to join that, just join that to give it to the model for predictions. That is a very serious problem that I can think of if this product is going to be deployed on a real system.
Yeah, sounds good. Thanks a lot, Changchi. It's really insightful.
Yeah, no worries, because yeah, when I was in school, like the data sets are relatively small, and those are just toy example for task to just practice, right? So it was not a big issue. But really, if you get into the career of data science, like you're really looking for a job, then the first thing you need to face is probably not modeling the data, not those statistics, not about the 99% accuracy. Is about whether or not you can fit this data into your machine or into your distributed system or whatever it is. That's probably the first issue you need to deal with. And the second thing is that after you fit in this data set, how you can pre-process that in like a few minutes or a few hours instead of like pre-processing a data set for a whole month, right? So that is something we need to consider about.
Okay, yeah, sounds good. And I don't know if any other people have questions. I think most people have left, and Ashley and Sean, if the two of you don't have any questions, I think we can close this.
Thanks for showing this to us. It was great.
Thank you, Ashley.
Yeah, it's honestly such a great demo, and thanks so much for your time.
No worries at all. Thanks for having me here.
Thank you, Changchi. Thank you all.
All right, cool.
no worries.
Changchi, have a good day ahead of you, and for the rest of us, have a good evening.
Thanks. Have a nice
Thanks.
weekend,
Thank you,
everyone.
guys. Have a
Thanks.
good weekend.
Bye.
Bye.